All right, here we are. This is the third part, so installment C of 8.4, which is graphing trig functions, like sine, cosine, tangent, and their reciprocals, cosecant, secant, and cotangent. This one, in 8.4b, we learned about the parent graphs, as in like what happens when they're not messed with at all. But now we're going to look at what happens when we do transformations of what we call sinusoids. So sine and cosine functions are considered sinusoids. That's what we call them. So to begin with, I just wanted to kind of do a little breakdown of how the different placement of the transformations like affects the algebra behind what's going on. So first we're going to look at this y equals 2 sine of x. So 2 sine of x, remember, this is like when you have just 2x. And when you have just 2x, that's really a multiplication. It's saying we have 2 x's, like 2 times x. So when we have 2 sine of x, it's the same thing. That's really a multiply right there. So I put a little multiply symbol to remind myself there. But if you just have a number sitting right in front, that just means multiply. So what I'd like to do here is I want to kind of compare what the parent graph of sine of x looks like and how this 2, how that 2 transforms, like how that's going to change this graph. So first, let's just look at regular sine of x. So I made this little chart with these x's are angles. And then we're going to look at regular sine of x, so the parent function, and then we'll see how 2 sine of x changes. So let's fill in some values for sine of x first. Whenever we're thinking about sine or cosine or anything, we're always thinking about that unit circle. So I'm going to go ahead and draw that unit circle. I can hear pretty close, okay? And remember, sine, the function sine, is measuring, as we walk around the circle, we always start on the right-hand side. As we walk around the circle, we always go counterclockwise for some reason. How far up or down from the x-axis are we? That's what we're measuring. So at 0, this is where we're sitting, well, we are not up or down from the y-axis at all, so our sine value is 0. Then at pi force, that's the next one I picked out, pi force is a quarter of the way around the top. Remember, pi gets us halfway around, that's 180 degrees. So that means halfway, the top is pi halves, we have 3 pi halves on the bottom, and then pi force are the smaller subdivisions. So at pi force, this is kind of the weird one. This is square root 2 over 2. So you can use your unit circle to find these. Remember, sine is the y value because y is up and down. At pi halves, this is the point we're at. That's the point 0, 1, because we are up 1 from that y-axis, that whole radius of 1. Okay, then I skip to counting by pi halves instead of by pi force, just to get an idea. So next up at pi, we're all the way to the left. Sine function counts up or down. We're not up or down at all, so sine of pi is 0. 3 pi halves is all the way down to the bottom, so we are 1 below, so our sine function is -1. And then back at 2 pi, we're back where we started at 0. Okay, so I'm just going to draw in my regular sine function. So it starts at 0. At pi force, we have square root 2 over 2, which is about 0.71. I'm going to go ahead and draw that about right there. Pi halves is up at 1. Remember that we talked about the 5-point pattern in the 8.4b video. So it's like mid, max, mid, min, mid. Okay, so the sine function goes up, comes down, all the way through. I'm going to do that one more time. This is bothering me. That was closer. Okay, so this is like our regular sine of x in this light blue color. So let's see what happens when we calculate 2 times sine of x. That's what this 2 times sine of x is. So 2 times sine of x for whatever x. So when x is 0, here's when x is 0, I have 2 times sine of x. Well, I already know what sine of x is, so this is just 2 times 0. Well, that's still 0. Right? So apparently at 0, this function 2 sine of x, which I'll do in orange, is still at 0. So it still starts in the same place. Okay, at pi force, I need to do 2 times sine of pi force, which is square root 2 over 2. Interesting. This 2 and this 2, that's like a fancy one, a multiply by 2 and divide by 2. Those are inverse operations. So this just leaves us with square root 2, which is about, well, let's see, we knew what half of square root 2 is 0.71, so double that will be about 1.42-ish. So at pi force, we had the point pi force 1.42 on our graph. So 1.42 is going way up here. That's interesting because, we shouldn't be more than halfway. Before, we were like trapped in between 1 and -1, but now we've already exceeded that. Okay, at pi halves, we need to do 2 times sine of pi halves, which was 1. So we actually get 2. So at that highest point, now we're up at 2 instead of at 1. Okay. All right, at pi, you can kind of see how this is going to keep going. We're going to keep doing 2 times this sine value. So 2 times sine of 0, or sorry, not sine of 0, sine of pi is 2 times 0, so we get 0 again. So by pi, at pi, we're back down at 0. And you can kind of see that this is just kind of stretching, it's messing with our amplitude. Just like my cat is messing with my bamboo on my desk. Cleo, get down. You cannot eat the bamboo. Over there. Okay. Excellent. Okay. And if we keep going, same thing here. We're going to have 2 times the sine value at 3 pi halves, which is -1, which just gets us -2. So every like output we have for our sine function, we just multiply it by 2. And same thing here, we'll have 2 times 0, which is still 0. So we go back to the middle here. So I'm going to connect the dots here. So in orange, we have 2 sine of x. Cool. Okay, so in orange, this is 2 times sine of x. So notice the zeros are still in the same places. The min and max is still like at the same x value. Like the max still happens at pi halves, the min still happens at 3 pi halves, but those min and max values have doubled, right? Our max used to be, or for our regular sine function, our max is 1, but now it's 2. So really, what we've done there is we've just changed the amplitude. The amplitude changed from being 1 to being 2. Okay, so that's what happens to sine of x. Things should go a little bit quicker now. I've already filled in and drew the original sine of x. So let's look what happens. So instead of having 2 sine of x, this is sine of 2x. So the 2 is now right next to, the 2 is now right next to the x instead of out in front, like outside of the sine. Now it's inside of the sine argument. Okay, so we have our regular sine functions. Here's our regular sine graph. What happens when we do sine of 2x? So this is really interesting. Okay, when x is 0, sine of 2 times 0, well, that's still sine of 0. And I know what sine of 0 is. It's 0. So apparently at 0, we still have the point 0, 0 for our graph sine of 2x. I'm going to graph this one in orange again. So we still have the point 0, 0. So we're still starting in the same place again. Interesting. Okay, but now sine of 2 times, so we're doing sine of 2 times x. X is pi force now. So sine of 2 times pi force. Okay, 2 pi force, that's 2 quarters. Well, 2 quarters is half. So this is sine of just pi halves. Well, I know what sine of pi halves is, but that's interesting. Sine of pi halves is right here. Sine of pi halves is 1. So apparently, we have the point on our graph, pi force 1. Interesting. So I'm going to draw in pi force right here. Here's pi force. Maybe I'll label that in black. Pi force is in between 0 and pi halves. And at pi force, we're already up here at 1. Interesting. Interesting. Okay, how about sine of 2 times pi halves? Okay, 2 times pi halves, well, that's multiplying by 2 and dividing by 2. That's just sine of pi. I already know what sine of pi is. It's 0. So apparently, at pi halves, our y value should be 0. Okay, we can keep kind of seeing how it's going. Sine of 2 times pi is just sine of 2 pi. Well, I know what sine of 2 pi is. That's 0. So apparently, I keep saying apparently, it's driving me insane. Pi By pi, we're at 0, back at 0. Okay, somewhere in the middle there, remember we're following this sine curve still, so it should still have that idea of a sine like mid, max, min, mid. So right halfway between these is 3 pi fourths. We should hit that min. So sine of 2x looks like this. So it just, it's like going faster. The way I like to remember sine of 2x is it's like walking around the circle 2 times faster. Two times faster. So if it normally takes 2 pi to walk all the way around the circle, if we're walking twice as fast, we're going to get done in half the time. So our period will only be pi for sine of 2x when it's on the inside next to the x. That's kind of interesting, right? So there's sine of 2x in orange. It goes around the circle at 2 times speed. Another way you could look at it, so you can kind of look at that as like, if it normally takes 2 pi and we're going twice as fast and only take pi, another way to look at it is in 2 pi, you could actually go around twice because you're going 2 times the speed. If you're going 2 times the speed for the same amount of time, you're going to go 2 times the distance, right? So you can complete 2 whole cycles in 2 pi instead of just 1. Okay, how about sine of x minus pi halves? So we've multiplied on the inside now. What if we add or subtract on the inside? That's what we're wondering here. So I have my regular sine already graphed here again and our plots. But what happens when we do sine of x minus pi halves? Okay, so first let's look when x is 0. Well, when x is 0, this is sine of 0 minus pi halves. That's just sine of negative pi halves. I don't have that on my chart, but if I think about that, here's my unit circle. Okay, negative pi halves, negative means to rotate the other way. So instead of doing my angle counterclockwise, we're going to start from this end and go, I don't know. We're going to start going clockwise. I got confused there for a second. So I'm going to take a clockwise turn or a backwards turn, pi halves. So negative pi halves is actually right here. It ends right here. Negative pi halves is the same as 3 pi halves. We could add 2 pi to it, right, to see. And what's the sine value there? Well, it's straight down, and we're wondering how far up or down are we, so it's negative 1. So I'm going to make that orange equals negative 1. So apparently we have the point 0, negative 1, which is interesting. So it's like we're starting at negative 1 instead. So at 0, we're at the point negative 1. We're graphing sine of x minus pi halves. Okay, alrighty. So when x is pi fourths, now we have sine of pi fourths minus pi halves. So this is interesting. This is like a quarter of pi minus half of pi. So we're subtracting more than we have. We're actually going to be left with negative pi fourths. Okay, negative pi fourths, once again, if we think of our unit circle, we're going to be rotating backwards pi fourths, so that's going to land us this way at like a 45-degree angle. And sine here is going to be that negative square root 2 over 2. Because we're down, or we're below the x-axis, it's going to be negative, and that's that square root 2 over 2, or square root 2 over 2. So this is negative square root 2 over 2, which is about 0.71. Negative 0.71. I keep doing that. Okay, so at pi fourths, I need to draw in my pi fourths. I didn't include that on my graph. That's halfway in between 0 and pi halves. Negative 0.71 is like here-ish. Okay. Alrighty. Next up, when x is pi halves, so we have sine of pi halves minus pi halves. What's interesting, pi halves minus pi halves, that's, taking away everything we have. So that's sine of 0. I know what sine of 0 is. That's actually this right here. This is sine of 0. So this is 0. So we have the point on our graph, pi halves 0. Boop, right there. Okay, and we'll just keep going right here. So we're going to have sine of, this is when x is pi, so sine of x, which is pi, minus pi halves. Well, if we have a whole pi and we take away half of it, we're left with half of it, so sine of pi halves. I know what sine of pi halves is. That's actually this right here, sine of pi halves. So this is 1. Okay, so I should have on my graph the point pi. When I plugged in pi, I got 1 as my answer. So pi 1. All right. And we'll do sine of 3 pi halves minus pi halves. Well, 3 pi halves minus 1 pi halves is going to leave us with 2 pi halves. But 2 pi halves is just pi. I know what sine of pi is. That's actually 0. Right? So apparently I should have, this is going to drive me insane. 3 pi halves 0 as a point. So at 3 pi halves, we're back at 0. Okay, look at what we've made so far. So we started at the bottom, now we here. Okay, we came up to the top. We're coming back to the middle. You can see this curve as it's coming through, right? It's kind of interesting. And you can see this pattern. Here's that mid, max, mid. And we're doing a sine curve, so we should still go now down and back up. So we could just keep kind of filling in. Where is it going to be when it comes back up? Well, we're counting by pi halves. So after 2 pi halves, we should have, that's 2 pi halves is, 2 pi, that's 4 pi halves. So this would be 5 pi halves right here. That's where we would be back up. So you can see this sine function. It's right here. That mid, max, mid, min. It's like we wanted it to start, normally it starts at 0, but it ended up starting right here. How far over did it move to the right? It moved over pi halves. So this was a shift to the right, pi halves. How can we see that in our formula? Well, look right here. We had that minus pi halves. Remember when it's right next to the x, it like goes the opposite way that you think it should. That's not a good way to remember it. But x minus pi halves is a shift to the right, pi halves. So we just picked up our sine function and it's shifted it over pi halves. So every single point, so the maxes happen pi halves later, right? The 0 happened pi halves later. This 0 happened pi halves later. The min happened pi halves later. Nice. Okay, last one here that we're going to look at, sine of x plus 2. You might be able to guess what's going to happen based on other transformations that we've done. I have my regular sine here, so let's see what happens. Sine of x plus 2. When we figure out when x is 0, I have sine of 0 plus 2. Well, this is sine of 0 right here, just, because of my table. So apparently this is just 0 plus 2, which is just 2. So I should have the point 0, 2. See how I avoided saying apparently right there? So I should have the point 0, 2. Bam, right there. Cool. Alrighty. For this next one, I have sine of x is pi fourths. So sine of pi fourths plus 2, which is square root 2 over 2 plus 2. It's like about 2 plus that 0.71, so about 2.71. 2.71 is about there-ish. Oh, but remember, this is pi fourths. I need to put pi fourths on my graph. There-ish. Okay, and then basically we're just going to take whatever this value was, that's our sine of whatever the x function is, and add 2 to it. So 1 plus 2 is 3, 0 plus 2 is 2, negative 1 plus 2 is 1, and 0 plus 2 is 2. So let's fill in these points. So I should have the point pi halves 3. Should have the point pi halves 3. Pi halves 3. I should have the point pi 2. So find pi up 2. 3 pi halves 1. And lastly, 2 pi 2. There. And you can see that nice sine curve in there. Very nice. Okay, so what's the difference from this orange graph to that blue graph? Well, it just went up, right? And how far up did it go? Bum, 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 bum. Normally our midline was, normally our fluctuating around 0, but now we're fluctuating around 2. So this was a shift up 2. And I like to think of it as like, I mostly think of it as moving the midline, and then like the amplitude stayed the same, right? We still wavered up 1 and down 1. It's just we were centered around 2. So when we went up 1, it went up to 3. When we went down 1, it went down to 2. Okay, those are the main transformations that we're going to deal with. We'll also have a reflection, and we'll talk a little bit more about the period, but I'm going to make that part 1, just kind of looking at how